So this is work that I've done with a team. At times the team has been a little bigger than this. We've worked cross-agency, but this is my team at NASA Ames. For those of you who don't know, NASA has 10 centers. Ames is one of them, one of the ones in California. And so the work has been with Katie McTeague and Tina Panentine and Megan Parisi and Shu-Che Wu. And Megan and Katie were hired around 2020 out of Carnegie Mellon's Human-Computer Interaction Master's Program. And they've ramped up on this work and are now deep experts in some of the content that I'll be talking about. Dr. Tina Panentine was chief engineer at Ames for about 20 years and retired, and then I brought her back to help with this. It's especially at NASA, where the kind of the domains that you're working in are engineering, and yet we're talking about human-computer interaction. So it's been a very good partnership with her. And then Shu-Che Wu is Dr. Shu-Che Wu is a researcher. Her PhD was from Ohio. She arrived at NASA at the same time I did, around 2000, and we've worked together. And similar background. Hers, I think, was a little more aeronautics, but also cognitive science initially, and then more recently now human-computer interaction. So, okay, so let me get started. So what I'm going to do is I'm not going to talk about design of any systems, nor necessarily solutions to HCI problems. What I'm going to do is, in a way, just tell a story about our efforts to characterize an HCI risk at an agency level at NASA for human spaceflight as we begin to go beyond low Earth orbit. Okay, and characterizing the risk is difficult for a few reasons. I mean, one, like as you'll see, or may I say right now, we capture very little of the data that we actually, would need in order to be able to go look back at, okay, how, when a problem happens, like on the vehicle, how do we solve it, right? That doesn't get, people just work it, so it's not easy to go get at that data and how often we have problems, et cetera. And then the other thing is that we're, as you can imagine, it's a strong engineering organization. NASA really, that's what we do, is engineering. And so the human side, as in all such cases, can be pushed out a little bit. But there are reasons why I think right now we're looking at a paradigm shift if we want to go beyond low Earth orbit. And so that's the story. And I think that hopefully it's convincing. Again, at the end, please feel free to kind of ask questions, push back, tell me what you think. So this is what we have ahead of us here. So we just launched Artemis 1, right? And there were some delays, right? There were, I don't know if you were aware of this, but it ended up being, I think, a 29-day mission around the moon, a very long elliptical orbit around the moon and back. So this is the first time we've gone back to around the moon since I think 71. Vicinity of the moon, right? And it was uncrewed, so nobody on it. As I said, it was delayed because of we had some engine issues and fuel issues, and kind of every time we would try to pressurize it. So it was delayed for a few months, and then it finally went. Artemis 2 should be coming up in 24, and that is a crewed mission, still no landing. And Artemis 3, which is currently scheduled for 2025, is a return to the lunar surface. And there, the idea is that we would go through about 2030 with multiple landings on the lunar surface to set up a base camp. That's what you're seeing here in the picture, all in preparation for Mars. And very much, at NASA, more than in the last 2-3 decades, there is a real focus again on Mars as an actual target that is that we're working toward, and that we're using these lunar surface missions in order to prepare for Mars. Okay, so that is, and it's starting now. Some of the vehicles are getting built now. for lunar surface, and contracts are going out, and all these things begin to affect the overall architecture of how we will, eventually go to Mars. And so some of the decisions made now will have long-term consequences. Now, when I say that we're looking at a possible paradigm shift, it is in part because when you think about going to Mars in particular, what ends up happening quite quickly is as you start traveling away from Earth, you start getting a communication delay with Earth, where that gets longer and longer every day you travel. Mars, you launch when Earth is catching up with Mars, right? So the Earth moves around Mars around the sun a little faster than Mars does. Kepler's law, right? So Mars is a little farther out. So as Earth kind of comes up and starts catching up with Mars, you launch. It'll, typically, unless you actually accelerate the vehicle, it'll travel about 17,000 miles an hour, which is breakaway speed from Earth's gravity velocity. And then off you go to Mars. It takes about 9 months. By the time you get there, Mars will have traveled almost to the other side of the sun, right? So at 9 months, it's really at around 11 something months that Earth and Mars are on opposite sides of the sun. And then the time that it takes for light to travel from one to the other is about 20 minutes. So at that point, your return communication back and forth is about 40 minutes, just light time, right? So there's no shortening that, right? You can change how you communicate the interfaces. You can send text instead of, video or audio, but it's still going to take the same amount of time. And that's something that's confusing to people even within NASA. They said oh, it's better to communicate this way and that way. Sure. But it's like saying over in the military, right? It doesn't change what you're trying to say, just makes it so you're not talking over each other. So as you start, heading off to Mars, the first thing that happens is you start getting these high latency communications that basically prohibit real-time operational and, engineering and medical support. The second is very quickly, you're out of range of resupply. And third is that there are fewer opportunities for evacuation or rescue. And the important thing about those three things is that is how we have actually mitigated. Those have been our primary countermeasures for the last 60 years of human spaceflight. And you have these additional challenges, both on the surface of the moon and Mars, right? So dust, partial gravity, dormancy, and we're going to leave equipment there and then have crew come back to it, both on the surface of the moon and on Mars, right? On Mars, just like in the movie The Martian, the idea is you're going to land a number of things there first, probably your habitat, your food, and your return vehicle, all that, and then get there. So you're going to be leaving things and then hoping that they're working when they're there. So a lot of increased mission complexity. And space station, so low Earth orbit, which is where space station is 8 minutes away, right? Now, typically it takes more than 8 minutes to get to the space station, like when SpaceX launches, or the Russians with the Soyuz, because you orbit around the Earth a bunch of times before you actually go and dock, just to get in the right alignment. But there you are. You're just floating in a vacuum. So it's actually a fairly benign environment in a lot of ways. It's cold and it's in a vacuum, but there aren't like dockings aren't that bad. It's actually easier to dock in space than it is at a port for ships, right? In bad weather, right? Anyway, so this is the challenge we have ahead of us: is that beyond low Earth orbit, we suddenly start not being able to really kind of have the ground there to support. So let's look at some of these. I'll go through this quickly, but if you look, the columns here are crewed missions so far, right? So Mercury and Gemini in the early 60s, and Apollo, Skylab, Mir, Russia, and the Shuttle, ISS, Gateway. Gateway's planned; it's not finished yet. It's like a little space station around the moon, and then Artemis 3, first landings, lunar base camp, and then Mars. Okay, and what you see, and here plotted on the left, and I understand these slides will be available, so you can look at it in more detail, but we've said, what's the longest flight time, longest surface time, longest, crewed mission, longest period without resupply, et cetera, right? So One thing that you should note all the way through, kind of certainly Mercury, Apollo, and Shuttle is that the missions were short. And for Mercury and Apollo, all the vehicles were one-time use. So let me just, I can lay this over it, right? So short duration and one-time use, or short duration and maintained on the ground. So the shuttle came back to the ground, and what determined how often the shuttle went up was really how long it took to maintain it on the ground. And it took a long time to maintain it on the ground because we did not design the shuttle for maintainability. And that's its own thing, which I didn't understand a lot about until about a year and a half ago, was design for maintainability. Now I know a lot about design for maintainability as we've started kind of going down that path. But you can have a really good engineering design that has zero thought to how you're going to maintain it, and that makes sense in a lot of contexts. And in other contexts, maintainability is everything, right? And how fast you can remove things. Think of a race car, right? I mean, that thing, they're highly tuned to being able to turn it around and get it back on the racetrack from the pit very quickly. And there are other vehicles that aren't like that, right? But the shuttle wasn't, and so it took a long time to turn it around. Or we've had our missions be long duration and easy access from Earth. Okay, so that has been our experience so far. So one-time use, short duration and maintained on the ground, or long duration and easy access from Earth, where easy access from Earth means we actually don't have to fix things up there very much. We just replace the whole unit. And that's 99.9% of how we've done things on board the space station is you just send up a whole new system, what we call an orbital replacement unit, ORU. Now, the current mission paradigm is that we basically control things almost entirely from the ground. And what you see here on the right is we have a lot of people, like 85 plus specialists with a total of about 660 years of combined on-console experience per shift. So 8-hour shifts, right? So 8 hours, 8 hours, 8 hours. That's about what you have at any given moment in time working. And you have the front room, which is what we're all familiar with as mission control, like that, what you see, on NASA TV or what you see in movies. And then there's a back room where you got more people talking into the ear of everybody's in that front room. And then you have the mission evaluation room, what's here, the MER, and which is even more kind of deep expertise into the systems. This is how we've run missions. We have near complete real-time dependence on the ground. We also, as I said, have frequent resupply of spare parts, and basically evacuation to Earth is possible within hours. This is from the space station. So in a way, it's important to note that we have a human systems integration architecture. And we called it an architecture because it's kind of just to give it that, it has a lot of pieces, a lot of different elements of the function. And it basically involves humans and data and communication tools and visualization tools, right? So I have access to certain information. I can communicate with certain people in different ways. And interestingly, if you look at the Apollo mission control room there on the left, around from 61 to 73. Well, in fact, yeah, sorry, and that wasn't Apollo in 61. It probably wasn't the Apollo room until about 65, 66, right? So, but then ISS, space station, 2000 to the present, and they're actually remarkably similar. You go look in there, you've got monitors in front of everybody, you've got a big screen in front of everybody. Everybody's got phones and paper and headphones and voice loops with which they communicate with each other. And in the back rooms, you've got access to data. Some of it is still paper. A lot of it is now electronic, sitting in separate databases. But that which has been stable, this human systems integration architecture, which we have used to actually have remarkably safe human expeditions into space for the last 60 years, changes as we go to Mars. Why? Because once you get out beyond near real-time communication, you can't do basically what we've done over the last 60 years. Right? And we'll talk about that a little more. So what is it that we do from the ground? Well, it's actually, when you look at it, it just seems like one giant kind of like, it's like you see all this, stuff going on, people talking at the same time, but really they're kind of, as we've sorted this out, and this is our own, breaking out of the pieces of this, right? So part of what can be done from the ground is direct commanding piloting, right? Space station is actually flown from the ground. Like when we go and we say, okay, we're going to basically, correct the orbit, which happens pretty often. Or you're going to reset systems, or you're going to restart the heating loops. That all gets done from the ground. Like on board, they're mostly doing science. So space station, the vehicle is flown from the ground. So commanding, you don't do so much piloting on space station, but in a way you do when you reset the orbit, is done from the ground. Oversight and guidance, which is a different thing. Now you've got the crew doing stuff like executing a complex procedure. They're fixing a system. They're taking it apart. They're putting it back together. The ground is there and says, okay, yep, next step is this. Okay, this is the right tool, right? And that's like, oh, don't forget to put the electrical cap on that wire. Decision making, which is a different thing, right? And we see it, and crew will refer to what they call big irreversible decisions. And if you ask the crew, they'll say, yes, the ground is really important in helping us with big irreversible decisions. For example, okay, you're going to cut that wire with scissors, right? And they're like, okay, once I cut that wire, it's not going back together, right? And, or at least not easily. And then they wait for the ground to say, yep, go ahead and cut that wire, right? And then problem solving really, which is, okay, really look through the data. Why could this be happening? Why is it still getting colder when it seems like it should be, like there shouldn't be anything flowing in that, right? These are all different things that get worked from the ground. And they will all be differentially impacted by, say, communication delay, right? But that's what this ground team is doing. And again, that is how we have kept crews safe for the last 60 years. So taking that first one, like I said, mission control, MCCH is Mission Control Houston. And that's how it appears in all the documentation is MCCH, call MCCH, right? And they constantly manage the state of the vehicle. So that's another really important thing. You see this picture of one of these zoomed in on one of the, controllers there, and you see Spartan, I don't remember what this, that particular, I think it's power. And you see that controller is sitting in front of 1, 2, 3, 4, 5 monitors, each with in the order of 10, 15 little screens showing data flowing. That's telemetry. The space station has 300,000 sensors, of which it sends 30,000 readings down every 10 seconds, right? And you have people monitoring it in real time. Now, their alarms set to, if something reading goes beyond above this or below that, but it's not, none of that is perfect, right? I mean, which is interesting too, right? And we forget, right? We're very good engineers, but we're not perfect engineers. And so just like in air traffic control, right? You've got real, humans sitting in that environment. Here you've got humans and they are busy and they're looking and they are catching things, right? I mean, if not, we would have gotten rid of half of that kind of, capability a long time ago, right? But that's how we do it, is you have people watching that telemetry 24 hours a day, in the order of 15 to 20 controllers watching that, right? Next, as I said, you've got oversight and guidance of complex procedures. Here you see extravehicular activity on the moon, when the crew were there. And by the way, for the moon and during Apollo, it's about 3 seconds return time delay, right? Com delay, right? So 1.5 seconds in each direction. Made it a little harder. One of the complexities for the moon now, and I don't want to divert into this too much, but if things go as they are going now, the deep space network, which is this large set of satellites and communication assets that we use to communicate with systems that are out beyond low Earth orbit, like the moon and Mars and anything that we've got out there in the solar system, it has slowed down for a variety of reasons. It's not that it has slowed down. It is that as it has expanded, they're a bit kind of the weakest link in the chain, and so you've got a functional slowdown. So it looks like comm delays for our upcoming lunar missions to the south pole of the moon might be more like 10 seconds, right? And there's a big question: what does that affect? Anyway, so you see oversight and guidance as being, again, like when you're doing something, and the EVAs, extravehicular activity, what you see here in the picture, those are hard. And they're, everything you're doing is timed because you're running out of resources, or, you've got a countdown on your resources, et cetera, right? And the crew get tired, and it's, very challenging. Decision support, like we said, like that is, you got a flight director who's kind of, the big integrator, but you've got all this support from the front room, the back room, the mission evaluation room, all feeding to say, yes, do that thing, or no, don't do that, or yes, we'll give you a procedure for that. And then problem solving, like we said, the flight controllers are constantly monitoring systems, they detect anomalies, and then people start working them. And especially every now and then you get a big enough anomaly that it's all hands on board. Everybody's suddenly very worried and running around with a particular problem. And I'll talk about those in more detail, because that's kind of the rub, right? A lot of the time with more comm delay, everything will be just fine. But it's once in a while, there'll be a problem where we've now got reduced capability on board. Can we deal with those problems? And then how often do those problems happen, right? And those are the things that I think have been largely misunderstood, right? Anyway, just to add here, right? So you get that's a picture from the movie Apollo 13, which I think, something we're all familiar with, right? The when they had to fit the round a round piece into a square, kind of because each vehicle had separate types of CO2 scrubbers, right? So that kind of problem solving is worked in the back room. So let me kind of walk through one example of something that happened. So the International Space Station has two cooling loops, loop A and loop B. They're actually not fully redundant. In 2013, there was one that's been fairly, well characterized, where cooling loop A shut down. And you see here, 223. I assume Universal Time might be Houston time. And then at 2:30, at 3 o'clock. And so you see that this is evolving fairly quickly, right? So initially what happens is, and I won't go through this in a lot of detail, but a whole bunch of alarms go off. So the first thing that happens is, the alarm shuts down there at 2:23. And then you start seeing in that middle row, alerts are going off. There are different kinds of alerts on board. Often anything that has to do with life support basically will sound an alert on board that is of the type that says there's an issue that is potentially threatening to the life of the crew or the health of the vehicle, right? So something that could be very damaging. So basically the ground started working this right away, in particular to restart the cooling loop. And the crew actually often don't even get notified. They're up, they're doing their stuff. They actually, in this case, did need the crew's help because they thought it was going to get too warm. So they wanted the crew's help in turning off equipment and moving equipment that couldn't be turned off to another part of the space station. So this whole anomaly actually lasted a couple of weeks in the end because it was a biggie. But it's one that a lot of people remember. It's one that actually was a close call in the end because there are three very bad things that can happen up there. One is rapid depressurization. You basically get a hole and you vent your atmosphere very quickly. Another one is fire, and the other one is something a poisonous contaminant in the cabin. This one was almost that. The cooling loops, what flows outside of the vehicle is ammonia, and it interfaces with then flowing water on the inside of the vehicle, and that's how you release heat out into you basically the ammonia is running outside, but you obviously have these heat interchange location where they're kind of running next to each other, and you're passing it's like a radiator, and you're passing heat from the water out to this very cold ammonia. if the ammonia gets too cold, you can breach the interface and get ammonia in the cabin, and you will kill the crew. And it looks like, basically, if you go back, there was a close call investigation afterwards, and it actually looks like the and this is how it's reported, that the interface actually did freeze, it just didn't crack. So this was a very close call. So we then took this and said, what would have happened if this happened on Mars transit? And what you see is, this is assuming, I think, a 20-minute delay here. So obviously, you see up top there in red, these are the alerts going off. And let me just highlight this. So you get very quickly the detection of 30 plus alarms in the first 30 minutes, right? And again, that is now being handled by a whole bunch of people on the ground. And it's an alert saying there's a potential loss of crew, loss of mission, what we call lock-lom. There's a potential loss of crew, loss of mission situation happening on board. Then a safing response happens. Begin pump recovery, start it up again immediately. And then you start looking at prevent downstream consequences, shed heat load, start turning things off, diagnosis, what's the problem? And then all of a sudden it starts getting too cold, and they couldn't figure out why. And it turns out that there's this one valve that was stuck open, and this was figured out like days later. But in the meantime, you've got procedures that aren't working, right? This was all handled by, again, a team of 80 plus experts on the ground, working in real time, directly commanding things and trying to turn things on and off. That is our huge challenge going forward, is how do we turn that 80 human capability into, say, 4 crew members? Because that's our plan. And one answer could be, let's send 80 crew members. Now, you'd actually have to send more because they need sleep. So you'd probably have to send 240, assuming that, they're, working 8 hours and sleeping 8 hours, right? But we can't. The 4 is all, the shape, the size of the vehicle, et cetera, makes it so that we're deeply challenged in that way, right? And I have some slides at the end, if we get to them, that point out that even in terrestrial applications, that is on Earth, now or back to Columbus, Columbus, they had 3 ships, 30 sailors each. They could make new masts on one of the ships, right? If one ship sank, they could have taken all the sailors from one off to the other one, right? They had some redundancy. They thought about this thing to the extent that they could at the time, right? Here, we're pushing on every single kind of countermeasure that we use on Earth, right? If like on the submarines that go down for many days, you take 150 sailors. Aircraft carriers have 5,000 sailors, right? And they're not sitting around on beach chair, right? They're busy. Some of them are doing operations, but a lot of them are just running that ship, right? When you have very few, you can only take very few, crew members, humans like Everest. You're in, you're out. It's very short, right? And that's how typically we've done these, right? You're in, you're out. Or if it's longer, you try and send more people. The problem here is we're trying to cut, the number of people, the support from the ground, and you're in a big complex machine for a long time. So a total trip to Mars, 9 months each way, plus a stay there, minimum 2 years. So then we looked at what is the anomaly rate? How often do these bad things happen, like the one I just described to you? And it's high. When we looked at it, you see, and I won't go into the details, IFEs means items for investigation. This is one of the databases where you look to see the nature of these events that happen. But on average, about 1.7 times per year, you get these really kind of big doozy anomalies that are all hands on deck. Everybody is working on them. And what's worse is it was much higher, almost double that in the first few years, right? Because you don't know your vehicle that well. There are a lot of things that you haven't anticipated. That number is as low as it is because with Space Station, we've now been flying it for 22 years. So we've gotten to know the vehicle a lot better. And again, the way we mitigate it, the reason we haven't had loss of life or et cetera is because we're flying it from the ground. What's even more worrying is you look at this ISS class 2 alarms, and this means, like I said before, it's not an actual fire or rapid depressurization or something toxic in the cabin. It's one below that, which means take immediate action to avoid injury or death of crew or damage to the space station, right? what's it there? The 222s. I don't know why it's getting crunched a little, but that's the year at the bottom. So it's by year. And what you see is 660 total such alarms. This is as of 2019. We haven't counted the last few years. An average of 29 per year. So about every 12 or 13 days, there's actually an alarm telling you have a potentially lock launch situation, right? That's how often kind of the bells ring saying that you have a problem. And then above is about, maybe on average twice per year, but at the beginning, 4 times per year, it's real. So every few months you have like a real issue. A lot of the class 2 alarms are, often false alarms, but you got to respond to them as if they're real. So that is what the crew are going to have to deal with now more independently on their way to Mars. And we looked at Apollo, and the numbers are much higher, an average 3 per mission, where each one of those missions was on the order of 12 days, right? Total. And so, and why is that? Well, because there was a lot more going on with Apollo. You had, ships, vehicles coming and docking and landing and coming up, and you're on the surface of the moon, right? Now, none of this is surprising, right? So when you have complex systems, you have these hard things. There's no getting away from that, right? So, we looked at oil, deep sea, offshore oil rigs, right? And in fact, we talked to somebody who does, systems for oil rigs off the, in the North Sea off of Scotland, right? And, again, it's the same. And we were very interested in talking to the oil companies because they have a lot more money than NASA, right? And so I was like, okay, I'm sure they want to take care of their toys, right? And not have these things, being destroyed and et cetera, causing these major environmental issues. But no, if you look at the rate, and I'll have a chart in that in a sec, of these kind of problems on oil rigs, it's actually, it's there too. The Northeast blackout, 737 MAX issue, Tesla autopilot. Again, we're good engineers, we're not perfect engineers. This is US launch systems. At the bottom in pink, you see the anomaly rate from 1957 to 2014, right? So you see, we've gotten better. So it's not quite as high, the pinks. And then the little dark reds are when we've had loss of life. But, it's not like it doesn't happen anymore. We're still blowing up rockets every now and then, right? Here's the one I said about oil rigs, right? You see loss of life events and near miss. And again, they have money, right, to throw at these problems, right? And so these are, we're not going to engineer a way out of it. Maybe I won't spend too much time because I do want to leave a bit of time for questions, but we looked at, like I said, submarines, and you see there in green, 150 is the number of sailors, right? And by the way, the color reflects mortality rate. So subs, low mortality rate. Antarctic winter, about 250 people spend their time down in McMurdo Station in the Antarctic, very low mortality rate. Deep sea oil rigs, little risky. LCS, the littoral combat ships, they've had a lot of issues. 45 sailors. The whole idea there was to make a ship that could be sailed by half the number of sailors, a third of the number of sailors, and it's been a disaster. Interesting. As an HCI lessons learned, if you go look up the littoral combat ships, they're very interesting. Aircraft, you see there like the dotted circle around it because 2 pilots, but you've got real-time air traffic control, right? In helping them. Everest, very high mortality rate. And then you start plotting Moon and Mars on this, and you see that, again, you're taking a small crew, putting it out there, and then you're really lengthening the comm delay, the evacuation delay, and then, the mission duration, right? So we don't really have solutions for this right now from our examples on Earth. And I'll tell you, we've talked to a lot of different areas, right? Everybody says, oh, if you talk to like I said, Antarctic, or people who do cave diving or whatever. Yep. Now this, I think to this community, here, it should come as no surprise, but this is from, it's really interesting. This is from a docket. The references here in 2013 to the National Transportation Safety Board. It was Amy Pritchett and Kathy Abbott who put this together. And a couple of interesting things. One is they noted that around 40% of failure modes, and this is with aircraft, commercial aircraft, About 40% of failure modes were unanticipated by the designers, cases where pilots have to rely on their knowledge, skill, and other aspects of airmanship to mitigate the risk, okay? Unanticipated by designers is amazing, right? Because again, what we try to do through our engineering process is we want to believe we have a procedure for everything, and we've worked it all out. 40%, even if that's off by, even if it's off by an order of magnitude, that's still like an alarmingly high number, right? That things that go wrong, when they go wrong and pilots have to deal with them, are things that you just didn't foresee. Even when we do our hazards analysis and our failure modes effects analysis, we have all these analyses that we do, probabilistic risk assessment, to anticipate this and build in ways of like controls. But you can't foresee everything. The other really interesting thing that they found, which most of us don't want to know, but basically pilots noted that they deal with something that was a potential safety issue 1 in every 5 flights. Pilots do, right? And yet the accident rate is 10 to the minus 9, which is unbelievably safe, right? So both of these is your humans are the resilience in the system. Humans are the safety in the system, right? So that's why, now I have this in here because it's why this is about, this is mostly within NASA. Everybody goes, oh, we'll automate this. Or like, yeah, the crew are just going to be reading magazines all the way to Mars. I'm like, in what world, right? Our engineering systems aren't perfect. We know it from every type of system that we have on the ground, and that the humans are the safety. So unless you make those 4 crew members do what we currently do with 80 around the clock on top of it, that's why we need a paradigm shift to go to Mars, to go, and in fact, probably to go to the moon. So let me just touch on this, and then I'll start wrapping up. When I give sometimes these presentations within NASA, I get a few comments back that I've started to, flavors of a few comments that I've started to just kind of, put together, and this slide has some of them, right? So one is aspiration to engineer more reliable, robust systems so that anomalies do not occur, right? So very often they'll say, we've learned a lot about flying things in space from the 20 years of the space station. And no, like I said, that's why we've collected all this data from oil rigs, from, launch systems in general, from aeronautics, right? Because the fact is, complex systems will have issues. It's just in the nature of it, right? So we're not going to be able to, basically, Artemis 1, it took us months to get it off the ground, right? We had launch delays, and these are complex things, right? So, but yet there are people who still think that, no, we've got it all, we've figured it all out. And yet, again, I was at Johnson Space Center 2 weeks ago, looking at the carbon dioxide removal assembly system with some of the controllers who deal with that. And no, that thing's still having trouble all the time. So even the idea that we've worked out all the kinks is actually not correct. Second is notion that artificial intelligence will address everything. That it's like, no, don't worry, Alonso. AI is really, it's look at where we are today. Yeah, look at where we are today with AI, right? I mean, the real progress we've seen over the last decade in AI is all machine learning, generally like large data sets. And it's really not machine learning, right? It's kind of machine guessing, and it's very powerful. It gives us a lot of pattern recognition, right? And again, Chat GPT, the flavor of the month kind of thing of, but no sense of like true, not true, and all that, right? And so I was on a AFRL, the Air Force Research Lab call about a year ago, where they had the top AI people in the country, and they gathered the top AI people, and they had it was over 3 days, and at the end of one of them, where they'd had it was like this panel of and I think it was Tom Mitchell from Carnegie Mellon was the last one, and everybody was talking about what they were excited about in AI and over the next 10 years, and I think Tom Mitchell somewhat almost jokingly said, look, I mean, I'll feel happy if we have an artificial ant by 2035, right? Ants have about 100,000 neurons, and obviously, and every person on that panel agreed. They were like, oh yeah, that would be amazing. Okay, so there's a reality to where AI is and where it's going to be, so it's not going to solve our problems either. There's another one, which is that mission control, MCC, The Mission Control Center can continue to address anomalies even with delayed comm. No, like what we've seen through all our observation is that when you get these anomalies that are really substantial, basically, having real time is what makes all the difference. And then the perspective that training can be amplified to prepare crew to address, anomalies. For sure, we're going to have to change training. And in fact, each one of those, I'm not dismissing one, each one of those, the ground will still be there. We will have to train crew differently. AI will have to come in and help, where it can, and we're going to have to make our systems more reliable. And then other kind of misconceptions. One is SpaceX has a lot of autonomous systems. It actually doesn't. It is being controlled largely from the ground. Like when we send crew up on the Dragon to up to space station. As I said before, it's an 8-minute trip to low Earth orbit. Part of the reason that that's now commercialized and out there is because it's not, like it's understood now, right? It's like, okay, we know how to do it, so just make it like commercialize it so companies, we can advance, U.S. Companies that way. So, that's, there aren't magic solutions there. Also, sometimes I get back, like the space station crew already has a lot of autonomy, and they do, but that's because they're not flying the vehicle, right? I mean, everything's being done from the ground. So they're up there and they do their studies, and don't get me wrong, like what the astronauts do is remarkable, and every now and then they have to deal with problems, but really, like it's the fact that we've got this huge team of experts on the ground that matters when you have these real issues. Sometimes also we already know how to do a Mars mission safely, right? We've landed a bunch of rovers on Mars, but again, conceptually, like imagine like our job is like we had a student team here and we're trying to shoot a bowling ball at Mars. Okay, so we do that. Imagine you have to shoot similar size object, but it's a fishbowl, and you want those fish to get there not frozen and that enough oxygen and food and not scrambled, and you got to land them and right. I mean, so there is, when we send rovers to Mars, they're effectively off all the way there, obviously, and then when you land them, sometimes you bounce them on the surface, and then we don't have to worry about getting them back. And then, but about 70% of the vehicle mass and everything, when you look at, and probably higher when you're like heading away from Earth, it is actually environmental control and life support systems, right? So most of the complexity of a system that can't be turned off is actually what's keeping the crew alive. You need water, and that water needs to be clean, and it needs to be a certain temperature, it needs to be a certain pressure, and you need food, right? And that food needs to be, available and maintainable for months, right? And so it's an entirely different thing to try and do a human mission beyond low Earth orbit, and it's easy for us to kind of overlook that. Also, we have this notion that the Mars rovers themselves have a lot of autonomy. They have a lot of automation, but not much autonomy. In fact, the only thing that they do autonomously is navigate the surface for a few meters and avoid rocks and holes, et cetera. So this hazard navigation is, you give them a waypoint and they'll drive to it. So let me put this up as the last slide, and then I'll stop. And I really, it'd be great to get input and questions here. So as we move to longer communication delays, and so what you see in this chart, it's a bit busy, but the gray triangle at the bottom is the ground. The blue triangle at the top right is flight crew, right? So right now, with very low comm delay, what you're seeing across the bottom is Mission Control Houston maintains nearly full command of the vehicle from the ground. And that's with about a 1.5 second delay. As you move away and maybe go to, more than a second, well, already with a second, you can't do direct haptic control. You can't control, the robotic arm that's up on the space station. You don't control that from the ground. The crew control that. Because even a second really messes with kind of direct visual motor control. At what point does the ground stop being able to help with oversight and guidance of procedure execution? So the crew are now assembling something on the surface, and a hose won't reach from here to there. And the ground is now 10 seconds like delayed round trip. So they're not getting live input anymore. Does that affect their ability to now kind of help you out? And it's not just the once, it's, everything is, so, you could, sure, you can wait 10 seconds, but if it's a 5-minute procedure, and now you're turning it into a 50-minute procedure because you've inserted 10 seconds between every single action, right? That's the consequence. It's this ongoing delay, obviously. Somewhere in there, you move decision support off the ground and on board because you're no longer able to, the crew is no longer able to wait for the ground to give them these big irreversible decision support, right? And that, they might be able to wait 1 minute, 5 minutes, maybe even 10 minutes. We don't know. And that circle, but the big red circle is there's very little research in this area. And then at some point, you're going to shift problem solving on board too. Problem solving being like, why is it getting cold even though we just restarted the cooling? Why is it getting hot even though we just restarted the cooling loop, right? Real problem solving. Do you wait 20 minutes, 30 minutes, 10 minutes, right? So again, these are kind of notional, but so let me jump down here. And then this is a bit of summary of that data. And this is my last slide, but this is the one I want to end on. As we've started looking at these engineering and technology gaps, and this includes the question then becomes, how do we change our human systems integration architecture away from that one that I showed at the beginning, where the ground is doing all, we have a whole bunch of people, to shifting it on board. So first thing up at the top left here is simulation capabilities, right? We don't have at NASA, and really we don't have it anywhere on Earth, really good simulation capabilities for looking at complex anomaly resolution with delay, with ground in the loop, right? Because you're not going to get rid of the ground. And it's easy for us to forget that too. Everybody thinks, oh yeah, we need more totally autonomous missions. I mean, in some ways that would be great, but given that is a far, far from possible at the moment, let's settle with, having the ground do as much as they can and assume that, again, just per that previous chart that I was showing, that they're going to be able to do problem solving for you until you're really about 10 minutes, maybe 15 minutes away, right? So assume that, right? Don't try and make the ground don't try and make the crew on board do everything if the ground can still help you with things that aren't that urgent, that don't have a high cadence. We're going to, AI, and in particular for data monitoring, right? What I was saying, people sitting in front of those computers, looking at that river of data that's coming down, right? That's exactly where kind of the big data analytics can help, right? It's not going to help us on the engineering data side, for example, problem reports, et cetera, really understanding, no more than, we've been able to kind of crack that on the medical side, right? With intelligent diagnostic systems, right? Data integration is another huge challenge, and not just data integration and data architecture. And this has to do with the fact that even on the ground now, we have a bazillion different databases and everything's all over the place. Why? Because we can do it that way, and because each expert knows where things are. But once we start putting it on board, that gets a lot harder. And hugely important is data visualization, right? And this, how is, right now, again, you've got experts looking at data very narrowly in their area of expertise. And when we watch a movie like Minority Report, and you see, the main character interacting with, with hand gestures, that probably, won't be a thing, but interacting in a much more immersive way with data, where the data, maybe, we don't know, but helping crew be able to interact with complex data that's a combination of kind of the telemetry, the data flow from the sensors with your engineering data, which says, there's this part, and those two are close to each other, and this one has had a problem before. All this engineering analysis, how do you take all that and put it in front of the crew when they're trying to make decisions quickly? We have to support asynchronous communication. We have to change the way we do sensors. Right now, if it's getting hot, you get 30 alarms saying it's getting hot because all the sensors in that area detect it, as opposed to one alarm saying, hey, this whole area is getting hot, right? So data fusion, sensor integration, and then, virtual augmented reality for a whole bunch of aspects to it, it's getting to the point of kind of maturity where it's, relevant. And then maintainability. And this is something, like I said, that I've been deeply immersed in myself for the last year, because one angle of this is we have never really had to do maintenance in space, right? We either didn't use the vehicle again, or we did the maintenance on the ground for space station, or for the space station, we go and we just replace the entire unit. We've never had to fix like, okay, how do I just take this thing apart and really fix it at a more high resolution level? And then, certainly not on the moon either. Apollo 11 had no tools. They had a problem with an electronics board and they fixed it with a pen. These are the things as you slowly, so you go, yeah. So we've never had to, so now we're going to put stuff on the moon, leave it there, a whole camp, a pressurized rover, a habitat, communications, and solar panels, all this stuff. We're going to put it up there, and they're going to have to like first assemble it, then maintain it. And we haven't had to do that before. And so we've never had to design for maintainability, that problem that I was describing before. So let me stop there and take any questions, thoughts. And again, I hope that what I want to do was just kind of take you through all the kind of the data that we put together. And this is all internal to NASA. And I'm now the risk custodian for something called the Human Systems Risk Board. And this got made a red risk because we brought enough data forward saying these problems happen this often, they're of this nature, we solve it this way, but we've had to characterize the capability on the ground, the how often problems happen, to what systems they happen, all that just to kind of try and slowly turn NASA to say, yeah, as we start going to the moon and certainly to Mars, like the role of those humans who are now just four of them, more isolated, right? Not entirely, but more. Like there is no escaping the fact that we got to rethink our human systems integration architecture. So,